Hello again. This application today is called hydrostatic pressure. It is an engineering-oriented application where hydrostatic pressure is a force experienced by objects that are submerged in some sort of liquid. Oftentimes that liquid will be water, but it could be any other liquid substance. Some notation that you'll see rho, which is the mass density. That's the first underlined red line that I've got there. And that has units of kilograms per cubic meter, so the metric system. And you'll see delta, which is the weight density. That's the bottom long red line. And that is in pounds per cubic feet. You're going to need to get force, which is pressure times area. If you look at the highlighted equation, so if you solve for force, you'll have pressure times area, or rho GD times area, or delta D times area. Which of those rho GDA or delta dA versions you would use really depends on the units of the information that are given. And I'll try to highlight that as we progress through the examples. I've got in blue here some important foundational information, and that is the mass density and weight density for water. So water has a mass density of 1,000 kilograms per cubic meter, and in pounds per cubic feet, that weight density is 62.5. And so you will see me make use of both of those values in the coming problems. Let's take a look at problem 1. So the scenario here is that there's a dam that has the shape of a trapezoid with height of 20 meters. The base of the dam is 30 meters long and the top is 50 meters long. We want to find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top. You can see on the top left, I have a sketch of this dam. It's not quite to scale, but the general idea is there. The top is 50 meters long, the bottom 30. And we have that water in blue that's a little below the top. It's 4 meters below the top, which means that with the height being 20 for the dam, there's 16 meters of liquid of water pushing on this dam. Now in red, I put my frame of reference, and this is just what I chose, but you could have chosen something different. So I chose to put my origin at the center of that water level in the middle of the dam there, with X positive direction being to the right and Y positive being down. I could have kept it up, and I'll explain how things would have changed in that instance, but with Y positive being down, I'm going to progress through this problem. So in the first line, force is equal to pressure times area, as I said before. Since I am given information in meters, the metric system, I know that I'm going to be using the rho GDA version for force. Now rho is the mass density, which is 1,000 for water. G is your gravitational constant, which in meters per second squared is 9.8. D is depth. And since I oriented my frame of reference at the top of the water, depth being positive is down, so that's the positive Y direction. If I had put positive Y upwards, your standard form of axes, then depth would have been in the negative Y direction, and I would have used negative Y instead of positive Y here. So when I simplify, I have 9,800 Y, and area is going to be some width times delta Y. So look back at the picture there so I could explain that a little bit more. I could look at any tiny cross section of this dam wall, and in green I've got an example of it where I could view that cross section as a small rectangle with width W and height delta Y, because that's in the Y direction. So that's where the area of this rectangle, W times delta Y, came from in my force derivation here. Now, I'm comfortable with Y. I'm even comfortable with delta Y because when I integrate, that's going to be converted into a dy. It's the W that's throwing me off. What I notice, looking back at the dam picture again, is that that 30 meters exists throughout that dam. And what I don't know is I could view to the right and left of that middle part an A length. And so I have some distance A to the left of that 30, some distance A to the right of that 30 for any particular depth, which means that W is going to be 2A plus 30. So that's where that line comes from. Now, I need to figure out how to rewrite A, because that's bothering me. We just went from W to some function of A, and we still don't know A either. So I'm going to look at the thick black line that I put in on the right side, and I need an equation for that line, which means I need 2 points. I notice that the top right point is 25 comma negative 4. It's 25 to the right of the origin, and 4 up, but remember up is in the negative direction. Whereas the bottom point to that line is 15 to the right and 16 down, because again, down is the positive direction. And now using those 2 points and the slope intercept formula, I end up finding that y is equal to negative 2a plus 16. And so now I have an equation of y. I actually get it as negative 2x plus 46. I jumped ahead a little bit, so I apologize for that. But I notice that for any x, I could describe x as some distance a plus 15, because no matter what, I'm at least going 15 to the right plus some distance a. And so when I make that substitution in for x, I get negative 2a plus 16 is y. So that's that third red line or underlined red line area. Now, I'm going to use that to solve for a, which I do next. And I plug a equals 16 minus y over 2 in to the w formula that I put a dot next to up on top. The 2's cancel out, and I have 16 minus y plus 30, which simplifies to w is 46 minus y. So now I have y in terms of w in terms of y. And I plug that back in to the force equation that I had started setting up on top. So we have 9,800, y, w is 46 minus y, and because we're integrating now, that delta y becomes dy. And so now, when you integrate this and evaluate from a depth of 0 at the top of the water to 16 meters all the way on the bottom, remember that downwards is the positive direction again, you get 4.43 times 10 to the 7th, and this is in newtons because it's a force. So that's our answer for this first problem. Let's take a look at another example. And here we want to determine the force of the hydrostatic pressure on a cylindrical barrel with a radius of 3 feet that is submerged horizontally 10 feet underwater. So the way that I interpret this information is we have some water level. 10 feet below that is the barrel, the top of that barrel. And that means that since the barrel has a radius of 3, that the center of the barrel is 13 feet below the water. That's how I'm interpreting this. Now, for this example, I'm going to put our frame of reference right in the middle of that barrel. And so that means that the depth is going to go from negative 3 to positive 3 with standard axes. Positive y is upwards and x is to the right. And now I need to start putting together my force equation. So pressure in this case, since we have feet, is going to be delta times d, not rho gd. Delta, being that this is water, is 62.5, and depth is going to be 13 minus y. Now that's because y is going up from the origin, which is already underwater. And so if we go up from the center of the barrel, let's say 3 feet, so we're at the top of the barrel, that means we are at a depth of 10, or 13 minus 3. And so that's why depth in this case is defined differently. It's defined as 13 minus y. The advantage to putting our origin right in the center is because getting an equation for this particular circle is really easy. And I wrote that below the circle. It's x squared minus y squared equals 3 squared. If we had put the origin at the top of the water, it would be a different equation, which is a bit harder to deduce. So this leads to some simplicity. So we have pressure. Now we need area, and I'm going to look at my little green rectangle cross-section example that I have at the top of the barrel circle. And the width in this case is going to be 2 times x with a height of some delta y. And so that's where area equals 2x delta y comes from. Now solving for x with the x squared plus y squared equals 9. Equation or function is root 9 minus y squared for at least the positive half. And I'm sticking with just the positive half because by symmetry, the pressure on the bottom will be the same. And so in 2x delta y becomes 2 times the square root of 9 minus y squared delta y. And now we are ready to integrate. So formally, we would want to integrate from -3 to +3. That spans the full circle. Pressure is 62.5 times 13 minus y, and the area is 2 root 9 minus y squared dy. But by symmetry, we could just integrate from 0 to 3. That means we need to multiply by 2 of the same integrand. And I'm going to multiply through and separate this into 2 integrals, one with the 13 times the square root part and one with the y times the square root part. I'm going to pull constants out. And that gives me the next line, which is 3,250 times the integral of the square root of 9 minus y squared dy minus 250 times the integral of y root 9 minus y squared dy. From here, I progress demonstrating the integration. The first integral that I labeled number 1, I used trig substitution where y is 3 sine theta. And the second integral, I used u substitution, where u is inside the square root, 9 minus y squared. Feel free to pause the video here in order to study the integration. I'll let you know that for number 1, after I got my answer in terms of theta, I didn't use time in order to convert back into y, but I did convert 0 to 3 for y to a support for theta. And so that means theta is going to be the arc sine of y over 3 if you use the y equals 3 sine theta but solve for theta. And when y is 0, the arc sine of 0 is 0. And when y is 3, that's going to be the arc sine of 1, which is pi over 2. So that's where those bounds for the integration for number 1 come from. I did convert back to a function of y for number 2 just because it's much easier. And for each of those, the first integral I got 9 pi over 4, and the second one I got 9, which I then plugged in green in the top right for the 2 integrals respectively. And when you solve, you get approximately 20,723 pounds, and that is with actually evaluating pi as 3.14159. So I didn't keep pi in here. And that is